Okay, so Isabella and I worked on this paper or this method to actually solve a very high dimensional life cycle structural model. And the problem was when you get these variables, like even if you add 2 or 3 or 4 endogenous state spaces, computing these life cycle models using standard value function iteration and numerical methods is close to impossible. So the standard, I think Svedor presented a few days ago, the standard method to go to is this endogenous grid method, which allows you to use first order conditions to speed up the computation. You can avoid a whole bunch of numerical optimization procedures. But when our life cycle model actually had a whole bunch of discrete choices. Now, discrete choices are sort of isomorphic to non-convexity. And since the endogenous grid method uses first order conditions are no longer sufficient when you've got a non-convexity of econ terms, non-concavity of the value function. So instead of getting value correspondence from the first order conditions, we end up getting a sort of a value, instead of getting a value function, we end up getting a sort of a value correspondence on a non-uniform endogenous grid, which means that for each point in the state space, you can't compare different suboptimal points of the value function and eliminate them. You have a non-uniform grid, so you don't know if your point is actually optimal or not. And this method that we've developed is a scan method to recover the optimal upper envelope of the value function from the endogenous grid method. So in the talk, I'm just going to introduce an abstract setting, talk about why you get this non-convexity and why it matters, introduce an application, which is by Ishbikov et al. I think the front row of this order for it. For all the authors. We'll talk one slide and then I'll introduce the scan method. We'll talk one slide and the theoretical foundations and then conclude. Okay, so this is standard Bellman equation, right? What you have is VT equals some payoff today plus your value function tomorrow, and the control today C controls the state tomorrow via this transition function. You solve this thing on the right in the braces numerically, and the problem is when X, the state space gets very large, not even that large. Like we had a few housing, liquid assets, a few other states. This numerical step becomes very, very intensive. And we were already using one of the world's largest supercomputers here at AIM, and it was still close to impossible to do simulated method models. So the endogenous grid method is a standard method. You can express the equilibrium conditions in terms of functions that you know. You don't have this value function, the function that you know. So I'm going to quickly say the idea is you fix the state tomorrow as a uniform grid, then you're able to invert the Euler equation and get a non-uniform endogenous grid of the state today. Then you have a state today, state tomorrow, which satisfies the equilibrium conditions, and that allows you to get the value function. And we can do this in higher dimensions. There's a paper by Ishbikov 2014, which gives you conditions where this is not just a one-dimensional process. So what happens when we get discrete choices is, imagine now that we have a value function which is conditioned on the full sequence of future discrete choices in a dynamic programming problem. This can be finite or infinite, right? We're now picking a sequence of discrete choices, not just a discrete choice today. Fixing all the future sequence of discrete choices, the value function is going to be concave. But today, in your Bellman equation, you actually want to maximize over the combination of future. You're in a product space combination of these future discrete choices, which is this big bold B. The problem is this max operator doesn't preserve convexity. So even though these things on here are concave, this thing doesn't preserve convexity. So that's where the problem comes. And then the FOCs will mean this value function is no longer concave. So to conclude the introduction, this is related very closely to and builds on Ishbikov et al. Or the front row of this auditorium. And what Ishbikov et al. Do is solve this problem by picking out monotone segments of the policy function, interpolating the value function over that, and then developing the upper envelope. The main issue we had is that we had this sort of high-dimensional problem with a whole bunch of discrete choices which were imposed on me as a postdoc. which I couldn't get rid of because I have assertiveness problems. And we didn't know whether monotonicity could be satisfied. So the method we've got here doesn't require monotone policy functions. It's fairly general, and we proved that it works in a fairly general setting as well. And it's very easy to code. It's like 5 or 6 lines of code. I'm going to now demonstrate the model using the Ishkakov-et al. Demonstrate the method using the Ishkakov-et al. Framework example that they use. So we're going to think of a retirement choice model. People live up to time t, which can be any number. Each period, agents can choose to work or retire. Once they retire, they exit the workforce completely. Okay? If they work, they earn a wage YT. They can also save the wage into a liquid asset and earn an interest rate R, and they consume each period. If they don't work, they've just got the liquid assets that they have to live on for the rest of their life. And the work choice incurs a fixed utility cost delta. And you make the work choice today about whether or not you're going to work next period. And if you make the work choice, it's a discrete choice, you get hit by this delta term, right? Standard budget constraint, standard AT+1 AT, get paid, you consume something. Each period utility is given by your log and the delta term, which is the fixed cost. And we're going to assume log utility. Okay, so here's the Bellman equation as Ishkakov-et al. Write it, right? So this is the Bellman equation for the worker is maximizing over a continuous consumption. And the discrete, now the D prime is whether or not you're going to choose to work the next period, okay? And this is your disutility from working, and this Bellman equation here is, this value function for time tomorrow is conditioned on D prime. The point here is, as Ishkakov-et al. Write it, this value function, even conditioned on D prime, is not concave, because implicitly by choosing C, you're choosing A prime, which then implicitly controls the future sequence of discrete choices. So then you get this value function, even conditioned on D prime, is not concave. So if you take first order condition, you're not going to, it's not going to be good. Then there's a retiree value function, which is just standard. So this non-concavity, this is the non-concavity results from this is what Ishkakov-et al. Call secondary kinks. So another way to write this value function, which kind of talks to how I presented this Bellman equation in the initial setting, is to say, okay, instead of conditioning it on this period's work choice, we condition it on the sequence of future period work choices. And then this value function, which we can now call this Q function, is going to be concave. And what we're doing is picking the upper envelope of these future sequence of discrete choice specific value functions. And this is what we're doing when we pick the discrete choices. Implicitly, each period, so this D is a future sequence. And this value function is the upper envelope, and that's not going to be concave, even though these things here are going to be concave, which is the value functions conditioned with the future discrete choices. So we're not going to talk about too much, 5 minutes left. Euler equation. Get the Euler equation, you fix the next period state as the exogenous state. You then get this period state as the endogenous state, and it's not uniform. And we end up with something like this. Okay, so this is the endogenous states today. This is the value associated with the endogenous state, and this is a policy function. Because the point here is you have an endogenous state point and a value, and you may have more than at that C for this point x5, v5. It's not the optimal point, and we don't have another point on top of it to compare it to. So this is because it's the endogenous grid. So now the scan method that we've developed in this paper is saying, imagine now the first 2 points are on the upper envelope. Okay. Now we want to check if the next point is also on the upper envelope. If you move from the first 2 points, so from x2 to x3, and you make a right turn, and you don't make a jump in the policy function, you go from x2 to x3, make a right turn, don't make a jump on the policy function, means you're in the same future sequence of discrete choices, and you're concave, so you're still on the upper envelope. Now, what happens if you make a jump and you're still on the upper envelope? So what would happen is if you make a jump, if you change a future sequence of discrete choices and you make a jump and you're still on the upper envelope, it means a value function from below is about to overtake you or is just overtaking you. You're concave here, a steeper value function overtakes you, which means you have to make a left turn, right? And if you make a right turn and you also make a jump, it means you've gone to a suboptimal point in the value correspondence. So remember, we're talking about jumps in the policy function and right or left turns in the value correspondence computed by the endogenous group method. So this is very similar to, inspired by similar to Graham's scan, which calculates the convex hull of a set of points. Have 3 minutes?
Yep.
So we can show this like in an animation, right? So you calculate the gradient for this, the first 2 points. Then you compare the next 2 points with the gradient of the last gradient to make a right turn if the gradient is shallower. And you don't make a jump in the value function, you're good. You make a right turn, you don't make a jump in the value function, you're good. You make a right turn and you make a jump, sorry, not in the policy function, not the value function. You make a right turn in the value correspondence, you make a jump in the policy function, you're not good, you kick out that point. You make a right turn, you're making a jump in the policy function, you kick out that point. You make a left turn and you make a jump in the policy function, it's okay, you keep. And then make a right turn, make a jump, kick out, kick out, and you keep doing this. And you can apply this to every dimension of your database and get the upper envelope. So this is the example, a mixture of it all, we get the upper envelope, works pretty well. And this is the value of the policy function, value function on the right. This is the policy function practice, actually the mixture of it all. And we compute this for a number of examples. This is a Bella example, which has housing choice, a discrete choice of housing, value functions, just comparing value function iteration to what we've got. I don't have time to go through the proof, but all it basically depends on is we want the grid size to be big enough and we want these jumps to be detectable. If you can't differentiate a jump from then you kind of go nowhere. So these jump sizes have to be big enough compared to the grid size, and then the proof works to show that we can actually recover the upper envelope in a general setting using this procedure. Okay, so concluding, this is actually really interesting, more interesting than I presented it. So there's a no, it is also I'm on this applied postdoc, so I have to do applied work. But really, this is connected to 2 areas in maths. So mixed integer nonlinear programming. So the first way we tried to approach this was to try to look for necessary and sufficient conditions on the actual first order condition using calculus. And there's a bunch of papers that are trying to solve these types of problems in math. There's no like general setting yet. They have quadratic constraints and quadratic objective functions. But we were hoping to use some insight from economics, particularly monotone comparative statics, to give some structure, which could hopefully give these necessary first order conditions. This is further work. Another line of attack to this problem, which I think is very, very cool, is using convex geometry. So we can actually think about this problem as calculating a convex, like the inverse of a convex hull in the line point dual space, which is another generalization of this. But what we presented here kind of works for the just computing it. If people are doing SMN, please download my code and use